Well, last week's lecture 4 ended with the least squares estimation and a hint of recursive least squares and Kalman filter. So those are topics we're coming back to. But the next step on the syllabus is to stay with the basic beginnings, and in particular with eigenvalues. So eigenvalues and eigenvectors and their uses in solving initial value problems. So that's today's lecture, and I've written on the board the sort of the most straightforward the approach to eigenvalues. So let me take these steps. Here's the key equation. We're looking, what does it say? We're looking for a special vector x so that when we multiply by a, the result comes out in the same direction. I think of x as the input and ax as the output. A is kind of a black box. And normally, the vector that comes out heads off in some different direction from the vector that comes in. But for these special eigenvectors, ax is in the same direction as x, just multiplied by some lambda. And for example, if lambda is 1, then we have a steady state vector, ax equaling x. The same vector came out. If lambda is 0, well, then we still have an eigenvector. Notice lambda equals 0 is a little bit interesting. Ax is then 0, so that means an x in the null space is an eigenvector connected with the eigenvalue 0. Or lambda could be imaginary, complex. We'll see that for symmetric matrices, the eigenvalues are always real. And special facts, too, about the eigenvectors. Okay, so this is the idea. And the reason behind it, the reason it's a good thing, is that for these vectors, the matrix, with all its n-squared entries, is just acting like a number. If we can follow an eigenvector, then only that single number, lambda, is going to come in. It's acting like a 1 by 1. So it's terrific if we can find these x's and lambdas. So in principle, here's how to find them. First, just move that on to the other side of the equation. Now we recognize that we're asking this matrix here to be singular. This will if there's an x that it takes to 0, and of course we have no interest in the 0 vector, so we're looking for a non-zero x, then this matrix must be singular. Its determinant must be 0. And now we've got an equation. This determinant is a polynomial. It starts out with minus lambda to the nth power and other terms equaling 0. In other words, it's an nth degree, where n is the size of the matrix. You see what that determinant looks like? It has minus lambdas down the diagonal. So one of the first term in the determinant will be minus lambda times minus lambda all the way down, minus lambda n times, and then the other terms will involve lower powers of lambda. But we've got a polynomial, and it's got n roots. So these are the n roots. And those roots are the eigenvalues, and there they go. Okay. So that's the standard system. I just have to say, because this is a part of these courses, scientific computing, that you would never compute the lambdas this way, except maybe 2 by 2 I would. 3 by 3, that would give me a cubic. Well, unless it was a very nice cubic, I wouldn't even want to do a cubic polynomial that way. So this is sort of in principle, but to pack all this information into this determinant and then try to extract it is not the way to go. Is not the way to go. In fact, I could maybe, having started that, with a not, I should say, what is a better way to go? A better way to go is to, so let me hear a comment then on computing. Computing, we start with our matrix A and do operations on it. Maybe I won't give the details on that yet, but they're operations that don't change the eigenvalues. Just the way we did elimination steps and didn't change in AX equal B, now we do what we'll have to think. What are we allowed to do to a matrix that won't mess up its eigenvalues? We're not allowed to do elimination. If I subtract the first row from the second row, most likely I've changed all the eigenvalues. But there's steps that we can do, and we try to get it to a triangular form. Or even diagonal if it's a particularly nice matrix. Now, so you could say we did that before, but now this is going to be a form that has the same eigenvalues. So now let me ask, if I have a matrix and it is triangular, suppose it has A, B, C on the diagonal and D, E, F above, but zeros below. What are the eigenvalues of that matrix? I mean, part of talking about eigenvalues is to get practice with eigenvalues of important or convenient matrices. Okay, what are the eigenvalues? If we get the matrix into this form, or if we have this matrix, what are its eigenvalues? They're right on the diagonal. They're A, B, and C, right? Because if I took so that's an eigenvalue, for example, because A minus that times the identity. You see, what we're doing is we're really taking our matrix, well, so let me call that one A for the moment. If we subtract, we're sort of shifting our matrix to make it singular. Shifting by a multiple of the identity. And if I shift this one by a multiple of the identity, what do? I subtract A from the diagonal, and what do I have left? Well, for sure I have a 0 there, and something else, B minus A and C minus A. In other words, it's singular. There would be an eigenvector. In fact, it would be the eigenvector with that, looking at that column. What's in the null space of that matrix? Can you even tell me the eigenvector? 1, 0, 0, because when we multiply, you remember the key, when I multiply by 1, 0, 0, that just picks out the first column, which is 0. So there's the eigenvector, and there's the eigenvalue. Or one of the three, I mean. There were three. A was the first one, and similarly B, and similarly C. So that result gave us 0, 0, 0. Okay. So there we found an eigenvalue, and we found an eigenvector. So computing, and this was actually how to compute eigenvalues of matrices, let's say order 100. Then when I was in graduate school, it basically wouldn't have been possible to compute eigenvalues of 100 by 100 matrices. So this is really one of the successes of numerical linear algebra. How do you actually, in a stable, accurate, fast way, find the eigenvalues of a reasonable size matrix? Of course, the way I would find it now, I would be on MATLAB and I would type those magic letters, and it would list 100 eigenvalues. And if I wanted them in order, I would do sort of eigen of A, and so on. Anyway, and the way it does it is this idea of gradually moving to a triangular form. Okay, I think to give you details about that should come later. All right. So that's some comments on the computing. This is comments on the basic facts. Now let me come back to this is the central equation. That's what we use all the time. Let me use it in different ways. Let me, well, I have to make one comment, one mathematical possibility. Possibility is that some of these eigenvalues are repeated. We've got a polynomial of degree n. You know, a or b or c might be the same. We might, if a equaled b, then a question arises. If the a equaled b in that case, let me just go back to the matrix as it was. So if I have a triangular matrix, and I have, so my polynomial, oh, well, just tell me, what's my polynomial determinant of a minus lambda I? Just let's carry on this nice case. When this is my matrix A, I'm renaming the triangular one A. What would be the determinant? What would be the determinant of A minus lambda I for this triangular one? Well, we subtract lambdas from the diagonal, right? That's the minus lambda I. And we take the determinant and we get, well, product of these three. That's the beauty of the triangular part. A minus lambda, B minus lambda, C minus lambda. Because when I take a determinant, it's got a lot more terms, but if they'll all be zero because of those. So, of course, I see the three roots. No problem. And the possibility is that an eigenvalue might be repeated. Now, that raises various headaches, possible headaches. Everything might be just fine. On the other hand, it might be not so fine. By not so fine, I mean we might have A equal B, say a double eigenvalue, but we might not have two eigenvectors. Or we might have A and B and C, a triple eigenvalue. And we might have only two or possibly only one eigenvector. So I always have to sort of be concerned about that, or if I'm going to say something about all matrices, then those sort of degenerate cases have to be remembered. But for symmetric matrices, it won't happen. See, if the matrix is symmetric, then the above the diagonal would be 0, 2, and we'd have a totally beautiful example. So symmetric is good in this situation. Okay, all right, now back to here. Okay, so I'm going to suppose that there are n different independent eigenvectors, and I'll make them the columns of a matrix, x1, x2, xn. And I'm going to call that matrix S. So that's the eigenvector matrix. Can I put that in here? Eigenvector matrix. And I'm just going to do this matrix multiplication, A times S, and ask you what comes out. Okay. So what are the rules of matrix multiplication? I can do it A times the first column, right? That gives me the first column of the answer. And what is it? Lambda 1 x1, right. This x1 was an eigenvector we're imagining with eigenvalue lambda 1, so that A times that is lambda 1 x1. And then A times x2 is lambda 2 x2, and so on, lambda n xn. So the columns of A, S are very nice. But now I can do even better, do even more. I can write that as x1, my S matrix again, x2 to xn, times the matrix diagonal guy now, lambda 1, lambda 2, down to lambda n. Do you see that that works? Again, yeah, let's check the first column. That will prove everything. So we want to get lambda 1 x1 in the first column. Do we get it from here, from this? We do get lambda 1 x1? Yeah, because I'm multiplying this times the first column. And the result is lambda 1 of that and none of the others. So It is lambda 1 x1. So this is my S again. And this is my eigenvalue matrix, all zeros, called capital lambda. We get this nice, this is just the matrix form of that. Maybe I put two squares around it just to emphasize that it's really the same thing, doing all n at once. So that's the way. Now let me just jiggle a little. I could put the S, I could multiply both sides by S inverse. So I would have then A equal, getting rid of that S, we'll put an S inverse over there. Yeah, so that's maybe even nicer. That's one of the most important, that's the diagonalization of a matrix. So I'll put that word up, diagonalization. I started with a matrix A, and I ended with a diagonal matrix lambda, the eigenvalue matrix, that's this. And they're connected by the eigenvector matrix and its inverse. And there is an inverse, because I said if, there was an if in here, if there are n independent eigenvectors, then this eigenvector matrix will be invertible, and I'm okay. So this diagonalization it needs n independent eigenvectors. And as I said, that's guaranteed if the eigenvalues are distinct. If none of the lambdas are equal, then no problem. If there are some equal repeated lambdas, then could be a problem, or possibly not, depending on the individual matrix. Okay, so that was our goal there. And now could we practice on some eigenvalues? Just like we practiced on a triangular matrix. That's a real warm-up. How about a matrix? Let me ask you for the eigenvalues and eigenvectors of the matrix that we saw in the network problem, when there were 4 nodes and we had grounded one of them. I guess I didn't write down the numbers until the notes. So this matrix would be in the notes for lecture 3. So that came from lecture 3. That's the one with 4 nodes, and one has been already grounded. And so we have a 3 by 3 matrix. And I guess that's we could compute the determinant of k minus lambda I and expand it into a cubic polynomial and look for roots. Let's do it. Let's try to think of a better idea. Let me ask you, what could I shift that matrix by? So I'm going to shoot for the eigenvalues just sort of just by thinking, what are we looking for? We're looking for subtracting something from the diagonal that would make that matrix singular. And I think you can tell me one number that I could subtract from the diagonal that would make the matrix singular. If I subtract 4. If I subtract 4 from the diagonal, so k minus 4i would be what? It would be, if I took 4 from the diagonal, so you see we've shifted the matrix by 4, then the 3's become minus 1s, and you see we have a matrix which is it's quite singular. So there's an eigenvalue, lambda 1. And in fact, this example brings up, gets us really into it, because when I say very singular, what's a better way to say that? That's not a very mathematical way to say it. What kind of what would you say about that matrix? It's rank 1. Meaning, what about its null space? Because its null space is where the eigenvectors are, right? Null space is A minus lambda I, then here's the eigenvector in the null space of this matrix that we've shifted to become singular. Okay, how big is that null space? 2-dimensional, right, because we're inside 3 dimensions, but we only really have one equation here. So tell me we should be able to pin down a couple of vectors in its null space. So actually, this is 4 is going to also be lambda 2. This is going to be a case of a repeated eigenvalue, because that eigenvalue, that shifting by 4 produced 2 eigenvectors, a 2D space of eigenvectors. So we know it must have been a double eigenvalue. Not a triple eigenvalue, but a double. So tell me 2 eigenvectors that go with it. Maybe you can 1, 0, negative 1. So shall I call these x1, 1, 0, negative 1? And a second might be, you see you have quite a bit of freedom here. What would be a second eigenvector, also in the null space of that matrix? 1, negative 1, 0 would be another one. And you're really giving me a basis for that 2-dimensional null space. Okay. So we have found 2, sort of by inspection. Now what's the third? What's the third eigenvalue of this original matrix? Well, let's see. So we've lambda 1 was 4, and lambda 2 was 4. And now, when you only have one eigenvalue to go, you've made it. We have now. Why is that? Because the trace, the sum down the diagonal, which is 9 in this case, always equals the sum of the eigenvalues. So the sum down the diagonal, the sum of AII or KII, whatever matrix we've got, always agrees with the sum of the eigenvalues. That's the one pleasant linear fact about a nonlinear problem. AX equal lambda x is not linear because it's got lambda and x multiplied. But one nice fact, the sum of the eigenvalues, and this is called the trace of the matrix, trace of it. Okay, so what's the remaining eigenvalue? Must be 1, right? The trace is 9. We've already got 4 and 4, used up 8, so there must be an eigenvalue. If I subtract, what does that mean then? The third eigenvalue must be 1 from the trace. And now that means that if I subtract 1 from the diagonal, can I do that by a moment's erasing? K minus 1 times I. We'll change these 3's to 2's. And do we have there a singular matrix? We're supposed to, right? That's the check always. If you don't have a singular matrix, then you fouled up somewhere. Okay, so, but that is singular, and you can tell me something in its null space. In the null space of that matrix, because that's a vector we've seen before. It's a problem we've seen before, or a type we've seen before. Tell me a vector in its null space. 1, 1, 1. Okay, so we have found for that matrix, not in a systematic way, but anyway, successfully, 3 eigenvectors, 3 eigenvalues. 2 of them happen to be repeated, but it did not degenerate. Symmetric matrices, can I tell you some important facts now about symmetric matrices? Yes? Well, okay, so the question is, how did I know that this 4 was a double eigenvalue? Well, it was to do with the fact that you found 2 eigenvectors. And if you've got 2 eigenvectors, I darn well know that lambda had to be repeated twice. Yeah. Yeah, so the fact that this rank dropped all the way to 1. See, what's the rank of that matrix, just while we're practicing? What's the rank of that matrix? 2. It's not rank 3. Why not? Because it's singular. Right. It's not rank 1, certainly, because if it was rank 1, all the rows would be multiples of the same row. But that's not true. So we have that row and that row are independent, and that row is dependent on those because all 3 of the rows add up to the 0 row. Right. Yeah, it's okay. So what was I going to say? Okay. So K was we've now got K was a symmetric matrix to start with. And with a symmetric matrix, I wasn't worried. That is, I knew we would find we might have some repeated eigenvalues in this for this symmetric matrix, but I was not worried that we wouldn't come up with the eigenvectors, and we did. More than that, so let me go back. Can I go back to K? This one is singular, so 1 is an eigenvalue. Let me go back to the original K for some more comments. Okay. My comments then are about symmetric matrices. So the symmetric case. What's great about the symmetric case? And we see it here. First point about symmetric matrices, the lambdas are all real numbers. Here they were 1, 4, and 4. Good. Second point, and this is my new point, the x's, the eigenvectors, are perpendicular. Okay. So that's really terrific to be able, or I have to say, we can choose them perpendicular. Can be chosen because we have some freedom. Now, did we, look at these 3 eigenvectors that we picked. What's perpendicular to what there? X3 is perpendicular to 1 and 2. The dot product of that vector with that one is certainly 0. The dot product of that vector, which came from the eigenvalue 1, and this that came from the eigenvalue 4, certainly 0. We didn't quite do it right, though. Well, you see what we should have, I mean, if we wanted perfection, if we want perfection, then these two, this wasn't the perfect choice of x2. Do you see that I could fiddle around, so because I have a plane. This null space is a plane here. This is only a one-dimensional a rank 1 matrix, so it's going to have, and I'm in 3D, so I'll have 2 as we did, and within this plane of eigenvectors, why don't I choose a perpendicular pair? So this guy is fine, but I'm not sure quite how to do it, but what's a good one that's also in the null space of this, so it's also an eigenvector, but I'd like it to be perpendicular to this. 2 minus 1 minus 1. That would seem to work. 2 minus 1 minus 1. Is that perpendicular? No. Well, so how to fix it up for me? 2. See that my equation is making them add up to 0, which that did, but it wasn't perpendicular. Okay, let's try again. We need 3 numbers that add to 0. Maybe if I put the 2 in the middle, will that do it? Yes, because now the dot product of that with that is a minus 1, nothing, and a plus 1. So it is. Now, so that's the great thing then. That the x's are, or if I had space to write, or can be chosen because you saw that there was a little choice involved, perpendicular. And actually, now if we really want perfection, why don't we make them unit vectors? Why don't I make them unit vectors? Then, so I will divide that vector by square root of 2, divide that one by square root of 6, divide that by square root of 3. Those were the lengths of the 3 vectors. And now they have length 1, so they're now unit vectors. Now I'm totally happy with those 3 eigenvectors. And my comment is that as soon as I had a 3 by 3 symmetric matrix, I knew it was possible. I knew it was possible. Okay. And now I want to say, what happens to this diagonalization stuff? So we have the eigenvector matrix, and we've got the eigenvectors, we've got the eigenvalues. So why am I coming back to this result? Because I want to somehow identify or point to or highlight the fact that these eigenvectors, the 3 we finally chose, are perpendicular. In fact, they're perpendicular unit vectors. And there's a single word that says when you have a bunch of vectors that are perpendicular to each other, mutually perpendicular, and they're all unit vectors. Well, it's a basis for sure, but what's the adjective? Orthonormal. Orthogonal is the same as perpendicular. And then by making them unit vectors, we normalize them. So now these x's were orthonormal. So that's these ones I chose here. So now I'll erase this above. We've got orthonormal eigenvectors. Okay. Right. And I'll even give them a special name, a special letter, that which will be Q. Can I call those eigenvectors Q? Just, again, to highlight the fact that they're orthonormal. So I'll use the letter little q for a bunch of vectors that have this special property. Then it highlights it. So as a result, I'll call my matrix capital Q. So the result I'm getting to is that in the symmetric case, for a symmetric matrix, this A equal S lambda inverse becomes K. Can I use K for the symmetric matrix? And the point is that S is now, I'm going to use the letter Q. And then lambda, I'm staying with that letter lambda. And now here goes Q inverse. Right? I haven't done anything except to introduce the letter Q as highlighting the fact that the columns are orthonormal. So I used X's when they weren't anything special, but just independent. Now I'm using Q's to say they're orthonormal. But now there's something about matrices. There's something about a matrix whose columns are orthonormal. So these X's I can now call, these are now Q's. And there's something special about a matrix the matrix with those 3 columns. What's special about the matrix that has those 3 columns? Well, let me say, its inverse is its transpose. This is like orthogonal and even more orthonormal has so much importance through applied math. And here we're meeting it for matrices. So for matrices, Q inverse is the same as Q transpose. That's the, or I could say Q transpose Q is I. That would be another way to say it. Maybe that's the way to think about it. Why is Q transpose Q equal I? I'll make some space to multiply Q transpose by Q so that you see you do get I. Then that's saying that here we found the inverse because we found the matrix which multiplies Q to be I. So the inverse must be the transpose, and I'm especially happy to change that to Q transpose. And why? So this was the goal I was really after. I'll do that with large chalk. Why was that? Of course, sometime I pay the price by having to erase it. This is really a key fact here. That a symmetric matrix can be factored this way, into orthogonal times diagonal times orthogonal transpose. That's one of the most basic theorems of linear algebra. And why is it limited? How do I know that that matrix has to be symmetric? That I couldn't do it with an unsymmetric matrix, that this is really something special for symmetric matrices? Because the right-hand side is self-evidently symmetric, right? So the right-hand side is symmetric. Okay, so, right, and then I just wanted to complete this thought by asking you to check this Q transpose Q equal I part. So let me put that up above as the matrix multiplication of the year. So Q transpose times Q. So here's Q. So whatever it was, well, it was Q1 and Q2 and Q3. I'll shorten my life here. Okay. And the transpose will be Q1 transpose along that row, Q2 transpose, and Q3 transpose. So that's Q transpose times Q. And what are we hoping to get? I. And why? Because Q1 transpose Q1 is 1. That's the length of Q1 squared, so it's 1. And Q1 transpose times Q2 is that 0 there? And Q1 transpose times Q3, they're orthogonal, so that's 0. So orthogonal gives us all the zeros, and normal gives us the 1s. And then Q transpose Q is I, and we have square matrix. So if we have a square matrix, we're in business. We must have found the inverse. Q transpose must be the same as Q inverse. And, let me just throw in a comment connected, for example, to Fourier series. So there's a situation where we have orthogonal basis. Those sines and cosines are orthogonal, or the complex exponentials. We'll see Fourier a lot. Do you remember there's a formula to find Fourier transform, and then there's an inverse transform formula? And the point was those formulas are almost identical. They're just like transposes of each other, because there's another situation of that most desirable kind when we have things that are orthonormal, and inverting is just transposing. Ultimately, that's why we love orthonormal functions or vectors. Why we like to calculate with orthonormal things is that inverting is no trouble, it's just transposing. Well, from the scientific computing point of view, I think of another reason why we like orthonormal matrices. And that is that they never get out of hand. They can't, if we multiply together a whole lot of orthonormal matrices, Q's, well, it's still orthonormal and never grows. So numerical instability is never going to happen as long as we're dealing with Q's, right? Or these orthogonal matrices. Okay, so that completes the first part of the lecture. Let me, for a second part, give a second example, and then move to differential equations. And it may happen that this lecture the hour runs out before the lecture does. And then I'll start the beginning of lecture 6 with the completing the differential equations. I just wanted to take one of our earlier K's, or two of them maybe. So do you remember? Because my idea is to build this whole thing on those original matrices K. So let me take K. You remember the 2 minus 1, this one? And it would be nice to know the eigenvectors and eigenvalues of that one. Or do you remember B, the one that had both ends switched to, 1, minus 1, 0, minus 1, 2, minus 1, 0, minus 1, 1. That was the one that had both ends changed to 1. I could do the third one that had one end changed, but for time, let's... Okay. I'd be interested in the eigenvalues and eigenvectors of our favorite matrices. Okay. So let me leave a little space. These examples are so important. And what do we hope to do now? Well, we hope to see a pattern that's going to be true for all sizes, right? Because it wasn't just the 3 by 3 case that interested us, but n by n. And actually, the n by n example that I erased with the minus 1s filling all the above and below the diagonal, you could move to n by n on that one. And maybe the lecture notes asked if you could find the eigenvalue. So that would be certainly a problem. And feel that you could send me, a number of people send me comments or improvements. They're very, very welcome. Or new examples. Please go ahead. You could either send it just directly to me, so that's discrete, or put it on the Tech Ed, send it to everybody. That's less discrete, but both great. So please do it. Sorry? No laughing, right. That's right. Okay, so any eigenvalues for these? Well, tell me an eigenvalue for this one anyway. Do you remember about that matrix? Now this is taking you back 2 weeks. What was sort of special or maybe even unpleasant about that matrix? It was singular. So you know one of its eigenvalues already, 0, right. So the eigenvalues here are 0 and 2 more to find. Okay, and what do you know about the other 2 eigenvalues? Well, they add to 4 anyway. But I'm not, at a glance, I've forgotten what they were. Actually, I'm more interested in the eigenvectors. The eigenvectors of this matrix and the eigenvectors of this. And they're so important, actually. They're so important. Let me talk about an eigenvector of this one. This is totally special, right? I'm writing up a 3 by 3 matrix. I could numerically compute the eigenvalues of these matrices and the eigenvectors, or get MATLAB to do it. But we would miss the pattern, which extends to n by n. That's the only thing MATLAB, well, maybe not the only thing MATLAB can't do, but one of its limitations is that if we give it a matrix, it'll find its eigenvalues and eigenvectors, but then we say, just generalize. And MATLAB says, what? And doesn't know what to do. So let's do better than MATLAB here. Okay. Let me look at this one first. What I see there is, and you remember it came from that line of springs, I see this minus 1, 2, minus 1, this second difference coming up. And I see it's been chopped off so that the U0 and the U4, which nowhere appear here, it's as if they were 0, right? The 2 ends of the spring were fixed. This was fixed with U0 equals 0. And now I want to think of a vector that, I see, that'll be the pattern. U0 and U4, the end one's 0 and does something in between. And in between it does something, I'm just like proceeding by analogy here. Suppose it was a differential equation. Suppose it was a differential equation. This is sort of analogous to, yeah, if you're willing to give me this one. This is sort of analogous to looking at that. This is the second difference, and we'll talk a lot about that, or minus the second difference. So it's really analogous. So this is analogy. Equals lambda u. That's what we're looking for. Here, this is just by analogy. We're looking for k u equal lambda u. And k is like a second derivative, but it's really a second difference, true. And and it's as if u of 0 is 0 and u at the other end is 0, say pi maybe, or 1 or something, maybe 1. Could you tell me an eigenvector of the second derivative? Can you tell me a eigenfunction, I better say. Can you tell me a function whose second derivative is a multiple of itself? Yeah, you can do that. Sines and cosines. Sines and cosines. The second derivative comes out a multiple of itself. Actually, a negative multiple. If I differentiate sine twice, I'll come out with a minus sign, but then the minus sign will be there, so the lambda will be positive. Good. And now make it, now it's okay, any sine and cosine. Now, what one would satisfy this boundary condition? Or tell me one that would. So an eigenvector, or eigenfunction maybe, tell me a few, with sines would be good, right? Sines would be good because we want them to start at 0. And then we want them to end at 0 too. So sine, well, sine of t, but now what shall I fix? How shall I fix that there so that it comes back to 0, say at 1? Pi t. Pi t would be good. Tell me some more. Tell me another one. 2 pi t, n pi t. Right, any sine of something pi t. So sine of, in general, sine of n pi t. Okay. Yeah, so that would be the most general. And now I'm going to come back to this problem and say, well, maybe it works if I try uk equals sine of pi k, or yeah, k. Now t I can't use anymore. So let's see, t, k over n. Little n I've been using for the. I think that would work. The kth component of this is one eigenvector. This is first eigenvector. I have to tell you the whole vector. So I'm hoping that this works, that the kth component should be this. Now, first of all, does that satisfy our little hope that u0 will come out 0? Yes. And will un, u4, so this, let me make this clear what it is. I better make it a 4. Right? Because then u4 will be the sine of pi, and we already saw that that's great. That comes out 0. This is an eigenvector. Well, actually, I could write down what it is. What is that vector? Sine of pi over 4 is square root of 2 over 2. 0. So what's the sine of 3 pi over 4? Is it plus or minus? Oh, it's a 1. Oh, because the sine of pi over 2 is 1. Thanks. Right. And is it the same again? Yes, it doesn't switch. Okay. So that's an eigenvector. I guarantee that if I multiplied that matrix by that vector, it would come out lambda times that vector. Okay, so am I okay? Do I need a negative? Let's see. If this is if that formula, that would be one eigenvector. I think it might come out. It's a little hard to do the multiplication of that by that, but I'm pretty sure that will work. Now, I guess I ought to find 3 eigenvectors, and the way to find more eigenvectors was just to double the frequency and triple the frequency. So I could find a next eigenvector. A next eigenvector would be, so that was the first, maybe the second eigenvector will have components sine of 2 pi k over n. So what would it be? So again, k equals 0, fine, we get 0. Then k equal 1, I get, 4 always. I'm doing what MATLAB can't do and generalizing. Okay, the kth component of this second eigenvector will be, so the first component is sine of pi over 2. Is that a 1? And then when k is 2, I get the sine of pi. What's the sine of pi? 0. And when k is 3, I get the sine of 6 pi over 4, 3 pi over 2, which is minus 1. Okay. So I believe that's an eigenvector, too. And I believe it's perpendicular to that one. Why was I sure it would be? Because our matrix is symmetric. Because our matrix is symmetric, I knew I would get perpendicular eigenvectors, and I've got one more to go, and you can guess that it'll be the sine of 3 pi over 4. So let me, 3 pi k over 4. And what will that give us? That'll give us, when k is 1, we get this square root of 2 over 2. When k is 2, I get the sine of 6 pi over 4. That's 3 pi over 2. Is that 0? Is it? Or is it minus 1? Sorry, which is it? I'll believe anything. Minus 1? Is it minus 1? Sine of 6 pi over 4? Okay. And then 9 pi over 4. What's that one? Square root of 2 over 2? Okay. Now we can just check that these come out orthogonal. They really do. Yeah. And finally, should we check that? Now you see what's a little unusual here. I've guessed the eigenvectors without stopping for the eigenvalues. I didn't do it in the usual order. And I think these are the 3 eigenvectors, which I wrote in a row, but previously we were writing them in columns. Could I just, what's the eigenvalue for that guy? If it truly is an eigenvector, then I should be able to multiply by k and get some and stay in the same direction, right? That's what an eigenvector would do. If I multiply that matrix by that 1, 0, minus 1, I could write it up here to make that easier. 1, 0, minus 1. This is our eigenvector. Can you do that multiplication? What happens if you do that multiplication? What do you get? 2, 0, minus 2? Yeah, 2, 0, minus 2, so the eigenvalue is 2. Right. The eigenvalue is 2. And there's a nice formula for the eigenvalues as well as these nice formula for the eigenvectors. I can tell you what the eigenvalues for this matrix are. There are 2, which we just figured. There's the smaller one, 2 minus root 2, and there's the larger one, 2 plus root 2. Oh, and that reminds me. Somebody in the class had the brilliant idea. So you see, that's kind of nice, right? 2 and 2 minus root 2 and 2 plus root 2. Somebody who was using Mathematica, which is allowed, even if Cleve would disapprove. It turned out highly interesting. Use Mathematica or MATLAB, you'd have to use the symbolic toolbox to see the point. But it was something completely new to me. So just by chance, I think, found the eigenvalues in the 3 by 3, 7 by 7, 15 by 15, 31 by 31, one less than powers of 2. I don't know why it happened that experiment got done, but the results are sensational. Let me get those results onto the web page. The eigenvalues of that subfamily, K3, K7, K15, K31, came out with an incredible pattern, which I pose as an exercise to explain. Okay. Main point. This has very nice eigenvectors, and we can even guess them and check them before finding the eigenvalues. Good. And those eigenvectors are signs, discrete signs. In fact, they go into the discrete sign transform. The DST, the discrete sign transform, is the Q column, is this matrix with the eigenvectors of the columns, and they are these sign functions. Okay, wonderful. So that sign transform is quite important, only exceeded by the cosine transform. So the discrete cosine transform, the DCT, is of very great importance. It has been the standard for image processing. The JPEG standard for image processing has used the discrete cosine transform. That is, until this very year. Well, JPEG 2000, but they're running late, is the new standard for image processing and uses wavelets. So my later lectures on wavelets will connect directly to the IEEE, the new standard that's actually just voted on this week for using wavelets for image processing. But up to now, the ordinary JPEG standard, and we'll come back to that discussion, is the cosines. And where do the cosines come from? They come from this matrix. That matrix, because I've left the ends free. Remember that was the free hanging spring? So what's the boundary condition at a free end? The slope is 0. At the fixed end, U0 is 0. At the free end, the slope is 0. You remember, it came from, and so what if I change this to slopes, UT, being 0 for this? And then back in the continuous case, I'll use cosines, right? Cosines would be the functions that would be the eigenfunctions when we're using a 0 slope boundary condition. And do you see that maybe, and this is going to be part of a lecture, do you see that this 1 minus 1 row corresponds to saying 0 slope? Somehow that 1 minus 1 is a first difference. A first difference, where in the middle here we have second differences, and here a first difference again. Let me just capture this idea then. So what do I think is the eigenvector for eigenvalue all zeros? Oh yeah, you know that one. So the eigenvector for the 0 eigenvalue is, what's the vector in the null space of B? 1, 1, 1. So the eigenvector, this lambda equals 0, corresponds to 1, 1, 1. So that's cosine 0, I guess. Repeat it, right. Now there are 2 more eigenvectors. Let me look up the form of the eigenvectors And I'll erase this one. But, well, I won't erase it because that's the most important eigenvector. In signal processing, image processing, this, you want to have this eigenvector. You want to have that basis function because that's the DC term. That picks up all the constant background is picked up by this constant vector. So we'll make sense of these statements when discussing image processing. But it's beautiful to have that vector in the basis to be able to get the blackboard before I wrote on it, the whole blackboard in one vector. Where these signs are not so great because, as you see, they don't have the DC term. Okay, so I'm using the letters DC in two connections here. Discrete cosine transform is the DCT, and then when I said the DC term, that was like direct current constant. Okay, now, so just to finish, what are the eigenvectors? What are all the eigenvectors of this family, this B family of matrices? Okay, this is always one of them, right? We always have the columns adding to the zero column. Now I'm just need to tell you what are the others. So that was lambda equals 0. Let me bring that over here. This gave us the eigenvector 1, 1, 1. And now the typical lambdas and the typical x's. So I call them x's, or here I call them u's, okay? And I could have called them q's. Well, let's call them q's. Why not? Okay. So they'll be cosines. So how much of this formula can I remember? There'll be a cosine, and there'll be a pi, of course. There'll be a 4 in the denominator, and there will be, is it a k? Let's see, I'm looking, this is, do you see, right, there'll be a 1, 2, or 3. So there'll be a 1, 2, or 3, or no, 0, 1, or 2, damn. Is it 0, 1, or 2? I looked this up. Actually, just to mention, on this, yeah, this is better than trying to get it right on this little last corner of the board. I wrote a survey paper about the DCT, the discrete cosine transform, in Siam Review, and it would be on my web page. You could download the whole paper, and it would discuss the eigenvalues and eigenvectors of a whole bunch of matrices, of which this is the most important. There are actually several cosine transforms, but the winner, the one that people mean when they just say cosine transform, is the eigenvectors of this matrix. And the beauty is that, so that matrix is symmetric. So what do we know about those cosine vectors? They're orthogonal. And we can make them orthonormal. Right, that's right. So that's the point of that paper. So that paper is the discrete cosine transform, and shall I maybe take just a little space to put the so that's called the discrete cosine transform. It's in Siam Review. I think the year is 99, and the web page is www.math.edu/tilde-gs. And you would see it there, and you could download it. Or I'd be happy if you looked at Siam Review. I'd be even happier if you joined Siam, actually. Just completed a term as president. I think it's a wonderful society, and I take this improper moment to say that it's good. Okay, why don't we stop here? I didn't give you the I didn't complete this. There's a k plus a half comes in there, where a k happened to enter here, and it just comes out right. Just comes out right. So that's the discrete. These eigenvectors are automatically orthogonal. So the cube matrix with those eigenvectors is the DCT matrix. And to invert that transform, what's the inverse of Q? So this is a final question. It's its transpose, right? So the transform is very fast. You can use the FFT to execute it, and you get a highly useful transform. It's a real version of the Fourier transform. It's a real version with cosines. And the point about the cosines is they correspond to free boundary conditions. The sine transform has its uses too, and it corresponds to fixed boundary conditions. And in between, of course, we could have our t with a fixed free pair, but that's somehow not as important in reality as these two. So now we've computed the cosines, the eigenvalues and eigenvectors of the matrices that we have focused on. And then in the first part of the next lecture, can I use these while they're fresh in our mind to solve differential equations, and then speak about other topics, because the topic of lecture 6 is applied linear algebra more widely, but I'm going to be, this is a highlight of that one too. Okay, so let me stop here and pick up